All right, so you've been looking at acoustical interference between two sources, where we've got two waves spreading apart from different sources until they hit each other and interfere with each other. You can see in the 3D view that there are some places where crests are likely to hit crests and troughs are likely to hit troughs, and over here you can see regions of permanently high amplitude. Over here, crests hit troughs and troughs hits crests, so you can see regions of permanently low amplitude. If you're at a concert out in a park somewhere, you do not want to be sitting in this seat because you will not hear much, even though you're not too far from the stage. You can see the zones of destructive interference come in these incredible hyperbolic shapes. This is one of the places that hyperbolas occur in nature. You can see the focus points are right here where the two speakers are. If you move the speakers around into different positions, then you'll see a completely different interference pattern, and one that may or may not be to your advantage in setting up a concert. Notice you've got a very consistent pattern here, but these zones of destructive and constructive interference don't all stay in the same place. There aren't permanently bad seats and permanently good seats. There are places where you do hear volume in a fairly uniform manner. Play around with the different setups and see if you can get one you like. When you're ready, take the project indoors. Stop everything and clear the waves, and add a box. You want your box to be the whole room. So drag and make sure that it is the whole room with your speakers in it. Try the setup that worked best for you outdoors, where there were no walls for the sound waves to reflect off of, and see what happens with that setup indoors. It's all going to be fine. It's all going to be normal until one of the waves hits a wall. At this point, check your English. True or false, the wall interferes with the wave. Careful. Press play to check your answer. Write this down in your notebook, people. False. Walls do not interfere with waves. Interference is a technical term. Interference is what you get when one wave meets one wave and the two of them bang into each other. It does not mean get in the way of. When a wave hits a wall, what does it do? Pause, press play to check your work. When a wave hits a wall, it reflects, not interferes. When these waves hit the wall, they're going to reflect off the wall. Now, if you want to talk about interference, point out that there are two sets of waves here. One coming from the original wave source, in this case a speaker, one coming from the wall, that is to say the sound waves reflect off the wall and interfere with the new sound waves that are coming from the speaker. Let the sim go for long enough, you'll also see all four sets of waves, originals and reflections, interfering with each other as everything spreads around the room. Do you see any permanent zones of destructive interference here? No? Well, that's pretty good for the volume. Now, ask yourself, how is this looking in terms of sound quality? The interference questions in your lab are strictly about constructive and destructive interference, high amplitude and low amplitude. They don't say anything about sound clarity, which you can tell by instinct when you look at the picture. Is it a pretty picture full of mathematical patterns that are easily modeled, or is it an ugly picture that you couldn't possibly draw yourself and would have to take a screen capture? If so, you're not going to be doing anybody any favors in terms of clarity. Now, consider the acoustics of a gym. Play around. See if you can find some different setups that work better or worse, both in terms of volume and in terms of clarity. Ask yourself, anybody who's in sheer genius or has ever played in a band, what are the acoustics like in a gym? Is that the kind of sound quality you really want? Write up your observations and see what you can see about the acoustics. When you're done playing around with all the cool types of wave interference you can find in the menu and all the different structures you can add to try and model a real gym, Then head over to the virtual oscilloscope, the live one as provided on your Canvas links, and check it out. An oscilloscope is a machine that measures waves. It can be used for electromagnetism, and it can also be used for sound. I'm thrilled to have discovered this one here that can display to you the exact sound waves I'm making with my voice as I say them. Pause and play around with your voice. See what kind of patterns you can make. Then, when you're ready, get your notebook and your paper to take notes. Yes, you will be doing this live, and be ready to follow the instructions. Okay? Ready? Our big technological advance for the day is noise-canceling headphones. I'm very excited about this technology because my first year as a physics teacher in 2001-2002, when I was the virtual physics teacher at Academia Maria Reina in San Juan, Puerto Rico, I asked about noise-canceling headphones on my test, and 9 out of 10 of my girls circled the wrong answer. Not only is this fiction, it is ridiculous, it is impossible, it will never ever come to be, and the 10th girl, who was a child of 2 engineers, wrote, actually no, this is not only possible, it's already happened. And now when I ask who in my class has used noise-canceling headphones, everybody has used them. Most people own them, and I get them for free, cast off by the Spanish teachers who want better ones and are happy to have me have the leftovers. If you've got a pair of noise-canceling headphones at home, put them on, turn them on. Do not plug them into your computer speaker or your phone or anything. Not plugged in, just the noise-canceling technology. Pause, move around the house with them, and see what kind of noises noise-canceling headphones cancel out. Come back when you want to hear the results. Ready? If you didn't try turning the radio station to halfway between 2 stations, somewhere where you're just going to get static that goes, try that now. You'll hear a significant reduction in background noise. However, if you leave the noise-canceling headphones on now while you're still listening to the lecture, you'll find that you're still able to hear pretty clearly what I'm talking about. That is to say, the noise-canceling headphones work very well if you're trying to work on a plane, if you're trying to work in a very, very large office with dozens or hundreds of cubicles of people, all talking at once, more or less the same volume, in the constant din of background noise, but they don't seem to cut out sounds that are local, that are unique to you. Let's model how. In your notebook, explain how it is that you can cancel out unwanted noise. Not earmuffs, not drown it out, not block it out. Earmuffs or earplugs are made of an incredibly absorbent material. The sound comes in, it pressurizes the material. The material says, okay, I'm squishable, but I'm not very flexible. You want to pressurize me? Fine, I'll stay pressurized. The earmuffs or the cotton balls or the earplugs stay pressurized. They absorb the sound wave. They convert the vibrational energy of the sound wave to thermal energy, and that's the end of it. Once it's converted into thermal energy, it stays thermal energy. Once it's been used to do mechanical work by compressing those earplugs, that mechanical work stays done. We're not talking earmuffs. We're talking noise-canceling technology with pinpoint accuracy. Press play to check your work. You saw in the lab that destructive interference happens when you have one wave with, got to be clear, the same amplitude and the same frequency as the old wave, but played in reverse orientation. Check your lab and proofread, not opposite directions. If you have a crest from the left and a crest from the left, that's constructive interference. 5 plus 5 equals 10. Congratulations, you've just doubled the amplitude. But destructive interference, they can be coming from the same direction, but if they're a crest and a trough, 5 plus negative 5 is 0, and you can have 2 sound waves, 180 degrees or pi radians out of phase, and you should get 0. When you're ready, put your pencil to the paper and try to cancel out the noise I'm making while I'm making it. Notice that this has to be done in real time in order for the noise canceling technology to work. I will make noise, you try to cancel it out. In the middle of the demo, I'm going to freeze the live input just so you can see better. Notice how very difficult it is for me to keep a constant pattern on this screen, but the freezing is only going to happen for a few seconds for purposes of the demonstration, and then we're going to go on. Be ready. When I go up on the screen, you go down. When I go down, you go up. Look out for that brick! Sorry to startle you there. How many of you managed to get crests and troughs a decent share of the time for something that sounded like this with a consistent pattern? When we do it in class, in real time, I will go a lot more slowly than a real oscilloscope, but most people are going to find you were able to cancel out this and that, and this and that. You can try it now in slow-mo with the wave that's here. Press play when you're ready. The point is, when there is a sudden noise that you didn't expect and you couldn't predict, there's no possible way that you're going to cancel it out. Here's an important question. Pause to answer it. Were you really canceling out the sound wave that I was making while I was making it? Press play to check your work. No, you certainly were not. It would be impossible for you to do. You would have to predict the future as it becomes in the present. What you were doing is you were canceling out the sound wave I had previously made through a pattern of pattern recognition. You were operating on the assumption that the pattern that was down, up, would continue throughout the future and therefore enable you to predict the future. When all of a sudden a new noise came from, look out for that brick, that you couldn't predict, there's no possible way you could have canceled it out. It didn't fit the pattern. This is what noise canceling technology does. Notes: noise canceling technology has three components. Number one, it has a microphone to record the sound. Number two, it has a computer chip to take the sound pattern, flip it over the x-axis, not the y-axis, the x-axis, upside down, crest to trough and trough to crest. And three, it has a speaker to play back the modified sound. That's why your noise-canceling headphones also double as regular headphones. They have regular speakers in them. They can play music from your computer or for your phone, as well as canceling out background noise. The speaker is one of three parts. The noise-canceling technology has a time delay. It has a time delay in microseconds or milliseconds. It cancels out the noise that was and plays it now in hopes that the noise that was will still continue. Therefore, big conclusion, put a box around this. Noise canceling technology only works with constant, consistent sounds, namely a buzz, a drone, or a hum. Try it with your own voice here, and you'll see that the only consistent patterns are ones. Notice this, we're working in the hundreds of hertz, that's hundreds of times per second. Not consistently like here's your physics teacher who never shuts up, but consistently on the scale of milliseconds. That pitch doesn't change. When I began teaching, noise canceling technology had a very specific market niche, and that was workers on airport tarmacs who would soon be deafened by the roar of the engines, but still needed to be able to hear the planes coming and going and their coworkers shouting instructions, or they would be flattened into a work of modern art. That is why my Maria Reina girls hadn't all heard of them. The reason you all have heard of them is that the technology has discovered a new market niche, namely business travelers and people in cubicle farms for whom the roar of the engines and the constant din of everybody talking all around them is consistent enough that although the noise canceling headphones can't predict every sound, they can take a large bite out of the amplitude of the constant drone of the background noise. Please note that noise-canceling headphones have speakers in them. They are not cutting the noise. They are playing extra noise to go with the first noise, and thus they can be dangerous when turned up too high. Now for the question from the beginning of the lab. What are these marvelous hexagonal works of modern art that are hanging above the stage? They're not just works of art, they're sound reflectors. The designers of this concert hall and just about every other professional music space, including recording studios, rehearsal rooms, concert halls, and presentation rooms, uses sound reflectors to manage the waves. They want constructive interference here where the seats are. And if there's going to be destructive interference, it might as well be 30 to 50 feet off the ground where people aren't going to be hanging out. You can buy materials not only to absorb the sound, but to reflect it to get constructive interference where you want it and destructive interference where you want it. And that is where acoustical engineers really get down to business.